So I'll show or highlight, we will discuss here the various challenges confronting to the use of these initiatives, especially in this part of the world, that's the Kashmir. These are the initiatives that have been launched. We'll discuss them one by one. First one is SIAM. It is an indigenous IT massive open online course platform for providing best quality education that can be accessed by anyone, anytime, and anywhere using an IT system. The concept of MOOCs involves online delivery of interactive learning content to large number of people simultaneously. It allows sharing of best quality education with everyone, thereby bringing in equity as far as the quality of education is concerned. There are four quadrants of this pedagogy, that's MOOC pedagogy. Here we have video tutorials, e-content, self-assessments, and the discussion forums also. For the students, SAM allows them to take part in various courses offered by the best institutions and offered by the best teachers in the country. And for the teachers, it allows them to undergo online faculty development programs like workshops and refresher courses. The faculty of higher education can utilize its services by taking advantage of the basic principles of education, that is access, equity, and the quality. So this module, the teachers module, aims to update the teaching skills of the teachers. The second one is Swayam Prabha. It has been conceived as a project for telecasting high quality educational programs through 32 DTH channels that are live 24 by 7 basis. Every year, every day, there is a new content of at least 4 hours, which would be repeated 6 times a day, allowing the students and the faculty to choose the time of their convenience. Besides other streams of the students, the DTI channels cover curriculum based on the course contents covering diverse disciplines such as art, science, and other branches. The Swayam Prabha telecasts various special sessions, particularly for the teacher training, which acts as the orientation or the refresher sessions for the faculty, which usually remain cut off from the rest parts of the country. There is another one initiative from the Ministry of Education, that is National Digital Library. National Digital Library in India aims to collect, preserve, and disseminate the entire intellectual output of our country and provide online access from school level to postgraduate level, including the technical education. Besides other things, the project aims to develop overall framework to collate large number of e-content for schools, colleges, and other higher educational institutions in the form of, the virtual library. At present, there are more than 4.5 crore items in the form of books and other e-contents, that in the form of a multimedia shape type content, that is available in English as well as in other languages also. Currently, the content is available in at least 10 different languages. Moving on to one more slide, there is another initiative, that is eShot Sindhu. A large number of international electronic journals and the ebooks are available to all the higher educational institutions through this initiative. This allows access to the best education resources in the world using digital mode. The research work of the scholars all over the country has been made available in open repository and can be accessed freely by anyone. The research work can be used as reference document by the faculty as well as the students for their research. So all the content is available in a single portal. There is no need to serve multiple portals for search of the research papers. One more initiative is the virtual lab. since physical distances and lack of resources make us unable to perform experiments, especially when they involve sophisticated equipments or the instruments. A virtual laboratory is an online tool for remote learning and performing experiments through web interface available anywhere on many science and engineering subjects. Using this initiative, a feel of real laboratory is being provided using an interactive graphical user interface. In this mode or in this initiative, we can repeat experiments many a times without any cost, and we can even use the sophisticated equipments that are not physically available in our institutions. And also we can perform the experiments anywhere. We can perform the experiments at our homes, colleges, and in any place where the internet connection is available, or we have an IT system in the form of a computer or in the form of a laptop. Moving on to one more initiative is it's a talk to a teacher. It This initiative is basically provide us free access to a few selected graduate and postgraduate courses that are taught in IIT Mumbai by the faculty there and by the scholars there. This initiative has been built or developed by the IIT Mumbai as an initiative of the National Mission on Education through ICT. It provides virtual classrooms to the faculty across the country. These courses can be viewed absolutely free of cost at lower bandwidth and using a computer or a tablet with a with an internet connection. So this is an important initiative by the Ministry of Education in order to achieve the previous ones that we have discussed from serial number 1 to 6. In order to achieve the full benefit of those initiatives, this initiative has been developed. And this initiative for the establishment of 1 Gbps connectivity to universities and 10 Mbps broadband connectivity to the colleges. Using these initiatives are under National Mission of Education using ICT. On the lines of Digital India initiative, the Ministry of Education has decided that the university campus having 1 GB bandwidth shall be made Wi-Fi enabled. Already, the IITs, IIMs, and NITs have been established Wi-Fi campuses. This initiative would really help the faculty to utilize the digital initiatives effectively and efficiently. In Kashmir, this initiative, the campus connectivity has been authorized to the Reliance Jio, and they have already installed few equipments in most of the degree colleges, government degree colleges of the J&K. There are few more other initiatives, that is National Academic Depository, ask a question, EHRA, and for free and open source softwares for the we can easily there are many softwares available that are free of cost, and are being and we can access these softwares using this initiative, that is the free and the open source softwares. Challenges for there are various challenges that hamper the use of digital initiatives for faculty development in the higher education in Jammu and Kashmir. Or we can I mean to say that in order to achieve the full benefit of these initiatives that have been launched by the Ministry of Education, the first one is we have infrastructural problems. We have here internet problems. The most problem frequent problem here is that problem of internet. We are using limited bandwidth internet here in the form of a 2G. There are frequent barring of internet services. Furthermore, we don't have so much sophisticated computers in the colleges. One more challenge here we face is the problem of electricity. And there is there is an important issue challenge that we may face is the issue of health issues. Using these using computers for a long time will result in various health issues, as we already know that. These are the few references that if we want to access these initiatives, we can use these references, or we can use we can go from the we can click on these references on these URLs to for accessing them or for using them. Thank you, sir.
Thank you very much, Dr. Parvaz. Uh,
Thank you, sir.
Up next is Dr. Junaid Shah. So,
Hello.
yes, yes, you are audible, Dr. Junaid. Please take your presentation.
Yeah, sir. Am I audible, sir?
Yes, you are audible. I'll be
Okay.
uh, Dr. Feroz also. Just Dr. Feroz,
So
please.
I will just try to share my screen, sir.
Please go ahead.
Sir, is my PPT visible?
Yeah, it is visible. It's visible, yes.
Okay. Assalamu alaikum to all of you. I will be presenting on the topic use of e-resources for promoting ICT education. Myself, Dr. Junaid from Department of Information Technology, Sri Pratap College. So, if we talk about ICT, what is ICT? Let's get to the basic definition of ICT. ICTs are nothing but the computing and communication facilities and features that variously support teaching, learning, and a range of activities in education. If we see at the term ICT, it's composed of three terms: information, communication, and technology. What is information? Basically, information is the processed data. When we process some data, we get the information. And when we get some information, that transforms into knowledge, and knowledge ultimately gives us wisdom. So first term is the information in the ICT. The second one is the communication. How do we transfer this information, this data, to some remote places? And third one is the technology. What is the medium? What is the technology that is used for transferring this data to remote places? The technology, the medium can be wired or it can be wireless. We say that ICT supplements blended learning. It's a combination of offline tools as well as online tools. So it's a blended learning. What are the various reasons for ICT growth? If we look at ICT, what are the various reasons for this ICT growth? Please go into slide. One second. Is my slide visible? Hello? Hello?
You are audible. Please
Yes,
continue.
yes, we are audible. Yes, you are audible.
Please tell
Slide.
me if my slide is visible in the full screen mode.
You are not using the slideshow as yet.
I have put it on the slideshow.
Dr. Feroz, are you able to see
Yeah,
that?
yeah, yeah. You are this time at reasons for ICT growth.
Yeah, exactly. I'm at this slide. So it's
Yes, exactly.
visible to you.
Yeah, yeah, it's visible.
Okay. Okay. So let's look at the reasons for this ICT growth. First one is the globalization of information. Information is available everywhere. But the problem is, how do we disseminate that information? How do we make it available to various places on the earth? Second is escalating demand for education in remote places. For example, we are not able to cater to many places in the world. We are not able to move into the remotest places of the earth or to disseminate information to those places on the earth. The problem is, how do we reach to those places? So this is one of the reasons for the growth of ICT. The ICT kicks in at this time, and it provides us with various tools and options so that we are able to cater to various people around the world which are located at the remotest, which are divided by various geographical barriers. One more bottleneck was that high-speed internet is required for ICT, but it was earlier this issue. But nowadays we have 4G internet, although it's not present in Kashmir. We have fiber connections also. So this fiber connections, this 4G internet, this overcome the earlier bandwidth issues. Earlier we were not able to stream the live videos correctly. There was a lot of buffering. and the video could not correctly be displayed to remotest places, and those were all of the problems. But nowadays we don't have these bandwidth issues because we have high speed internet these days. Also, there is a digital revolution. For example, nowadays there is advent of cheap and affordable ICT devices. We have today there is a boom for digital notepads, tablets, smart boards, smartphones. Everybody is having smartphone in his pocket. The kids are having tablet computers. There are smart boards inside the classroom. So there is a digital revolution. So more and more voices were raised for the growth of this ICT. And also, the government is also pushing us for the concept of smart schools and smart classrooms under the Digital India initiative. The government is promoting the education should be imparted through ICT tools only. For that, it's providing us funding for establishment of smart schools as well as smart classrooms. Also, it's a very known fact that images can be easily used in teaching and improving the retention power of students, because we tend to remember images more instead of text. So through ICT we are able to show images to the students who are able to explain various complex diagrams or various complex biological processes through the images, which we cannot explain through the text or through on the blackboard, because the retention power is more in case of images rather than that of text. And it's very easy for teachers to provide audio visual tools through ICT, because teachers can make the classes very interactive. For example, if we are this time, for example, if we are using the Zoom platform for this communication, it's a very interactive session. I can show you videos through the Zoom platform. I can show you various images. I can show you animations to disseminate information, to explain complex things. But but in the normal classroom setup, I'm not able to do those things. Now, how is this ICT expanding opportunities, educational opportunities? Now, there are some issues. We'll see how ICT is providing solutions to those issues. For example, we have small or urban rural schools. We cannot cater to those schools. How is ICT providing solution to that thing? It's providing a solution by using interactive phone-in programs. Like, for example, we have Hello DD, in which students post various questions to the live questions on the TV channel. We have also educational channels like Vyas channel. We have Swayam portal, various portals, MOOCs, where online learning is supported, where various ICT things are where ICT tools are coming into play. Also, there is a flexibility in the learning schedule. For example, during the normal classroom setup, if there is a class for example from 3 p.m. to 4 p.m., we know that we have to attend this class from 3 p.m. to 4 p.m. We cannot attend this class at any other time. But in the ICT, it provides us a flexibility. We can just watch the videos, we can watch the video tutorials at any point of time during our flexibility, which suits our needs. At that time at which we are free, we can listen to those videos, we can listen to those video tutorials. So there is a flexibility in the learning schedule. Also, nowadays there is an trend. Also, there was some workshop some days back also on the use of virtual labs. How can we collaborate with various scientists across the border, across various geographical barriers? So how can we collaborate with those scientists which are performing some experimentation in Germany or Europe or in America? How can we collaborate with their work? We can collaborate by using virtual labs. We can access various virtual labs, and we can collaborate with various scientists and we can perform experiments jointly and in a collaborative fashion. Also, ICT is not a one shot training. It's available 24/7. We can pause the play, we can pause the videos, we can play videos, we can even listen to the videos in a repeat mode. It's not that the lecture is delivered and we cannot listen to that lecture again. We can just rewind the lecture, we can just pause the lecture in between. If we do not understand some concept, we can just skip backwards. We can just skip the video backwards. We can again listen to that video. It's not a one-shot training. It's available 24/7. It's available 24 hours a day and 7 days a week. And it promotes lifelong upgradation of knowledge. We can learn our entire life through the internet resources that are available to us. What are the various ICT tools for promoting, for improving policy planning and management? For example, with the help of ICT, we can just provide online admission systems are there. There is student information system, management information systems, database for maintaining staff, and welfare, for salary management systems. All these things we can achieve with the help of ICT. Also, for policy analysis, we have storage and analysis of data. For that, we can perform data mining and analytics. We can make various policy decisions. We can make various decisions of our organization, for our college, for our universities on that data by analyzing the various data. For example, how many students on a particular year had made admission, what were the reasons for the large number of admission, or for what are the reasons for very less number of admissions this year, what was our result, what was our throughput for the result, what was the lacking. We can make all these policy decisions by implementing various tools and technologies on the data using the ICT. Now, tools for ICT, offline and versus online. What are the various offline tools? What are the various online tools? So if we make just a comparison between offline and online tools, for example, for online, we have video conferencing, we have webcast, we have radio and TV broadcast, which can cater to a large audience separated by geographical borders. We have Google Maps, with the help of which we can learn various topics, or we can learn various geographical things, like which is the glaciers regions, which are what is the geographical setup of a particular country, what is the geographical setup of a particular area, how are streets planned, how are streets located. About various matters we can just click, which it's under the click of our hand that we can use Google Maps and check various things. There is a large repository like virtual notes. We have Wikipedia. We say Wikipedia is a virtual note because everything is available on the Wikipedia. If we want to gather, or if you want to extract information about anything, we just Google it and search it on the Wikipedia. It provides us like a virtual notes. We have digital ebooks, which are very cost effective. For example, I will provide you a link like pdfdrive.net, where you can find PDF of various books. You can download those books and can use for your own purposes. We can form Google groups for interaction, which provides a sort of a forums for question answer sessions, for posing question answer sessions. Or example, you have Quora website where you can
Sorry,
pose various
sorry,
questions.
sorry, Dr. Junaid.
Yeah.
Your slide is not moving. It got stuck at one place. It is just at the same reasons for ICT growth.
Oh, you didn't pause me in between.
Yeah, it's there. In fact,
Anyway,
Is it now moving?
yeah, now it's moving.
Actually, it happens with this full screen mode. Isn't my slide visible
Now
in this mode?
it's visible, but it was not moving. Now it is at ICT expanding education opportunities. It's now
Okay,
moving.
now
Yes.
I'm moving to this slide, the tools for ICT.
and please try to conclude now.
Yeah.
As
We are just
Okay, I
5 minutes
will try
now.
to conclude. So just five. Give me 5 minutes, sir.
okay.
Okay.
Okay, I will provide you with the links of some various web resources that are available to us, which we can use for our own purposes. For example, you have YouTube. You might be knowing that YouTube is owned by Google. It boasts around billions of users. Almost one third of all people on the internet use YouTube. It's the second largest search engine. There are a number of videos uploaded on YouTube every minute. 300 hours of videos are uploaded on YouTube every minute. It's the biggest resource for us, because we can use it for live streaming our webcast. We can create various YouTube channels for disseminating the information. Second resource you might have heard about is about NPTEL, which is an initiative by Ministry of Human Resource Development. It provides various web or video lectures which can be downloaded free of cost for engineering students, for in various branches of science, for as engineering, humanities, where you have a lot of materials provided by the various professors of IITs and IIScs. They upload videos there on the NPTEL website. You can access that also. We have spoken tutorial website where various free and open source software training is being provided in various open source technologies like Linux, Scilab, LaTeX. You can learn LaTeX on this website, and the beauties of this thing is that it's free of cost. It also provides a certification if you want to appear in some examination provided by this spoken tutorial. You're provided a certification by IIT Bombay. You can check this website also. We have eGyan Kosh, where you can download materials, like we had IGNO materials. We can download various IGNO web material as well as videos. Those IGNO modules are present there in the digital form, in the PDF form, which you can download from this eGyan Kosh website. We have also consortium for educational communication. It's also a web resource. It's basically 24/7 web channel where where various broadcasts happen during the day, where various lectures are delivered during the day on various topics, and it has viewers across millions of households and remote places. We have Khan Academy. It's a non-profit organization. It also uploads various materials or video lectures on various aspects of science, such as math, science and engineering, computing, arts and humanities. You can browse this website and check various resources. The resources are of two types: web content as well as video. You can check this website also. Also, you have MIT courseware. It's just like NPTEL, where the various video lectures of MIT professors are available, and those are very high class lectures. For example, professors from Stanford or MIT, you don't need to go to those places to study. You can just download these videos, which are uploaded by these professors of MIT and Stanford on this website of MIT courseware. And then you have EPG Pathshala, where you have NCERT books or NCERT material. You can check this website also. And for research, you can use the Shodh Ganga website, where there are various theses of Indian universities uploaded. Even our university, Kashmir University, uploads thesis on this website. And the second link is about Sci-Hub. You might have heard about it. It's a proxy website for downloading research articles from where you can download your research papers free of cost. And finally, you have Google storage available. You have Google drives. You have Dropbox, where you can which provides you an Google storage, which provides you storage free of cost, online storage free of cost. You can use these for storing your information and other things. So okay, I will just run these slides. Lastly, I will leave you with a quote that you are an ocean of knowledge hidden in a dewdrop. Thank you.
Thank you, Dr. Junaid, for your nice presentation on uses of e-resources for promoting ICT education. Uh, Please, you stop now sharing your screen.
Okay.
Dr. Feroz, we wholeheartedly welcome our resource person of this session, Dr.
Yes, sir.
Fozia, Professor in the Head Department of Mathematical Sciences, Islamic University of Sciences and Technology. She has already joined us. Assalamu alaikum. Very good afternoon to you, madam, and to all the participants. Are you able to hear
Walaikum
me?
salam. Very good afternoon and assalamu alaikum to everybody.
Welcome to this meeting, ma'am. Dr. Feroz Ahmed Bhatt is going to be the moderator for this session. He is one of the
Yes.
participants. I would request Dr. Feroz Ahmed Bhatt Saab to please formally welcome and introduce our resource person, Dr. Fozia Qazi. Over to you, Dr. Feroz.
Thank you, sir. Thank you. Uh, on behalf of the UGC HRDC University of Kashmir and on behalf of the participants and on behalf of myself, I welcome you, Professor Fozia Qazi, on this ongoing online refresher course in science. Uh, Professor Fozia Qazi is head of the Department of Mathematics, Islamic University of Science and Technology. She also holds there a post of director DICA. Uh, she has done her PhD from Syracuse University in United States of America. She has worked as academic in the United States for many years before returning to Kashmir in 2009 when she joined IUST. Her current research uses the mathematics of symmetry, analysis on the shawl, lattices, and other traditional patterns of Kashmir to understand cultural order and interactions in the region. Uh, Her main contribution is that she introduced the actorial mathematics at Islamic University, for which Islamic University is one of the unique university in J&K. It's in fact the major contribution of Professor Fozia. Uh, with this brief introduction, I welcome Professor Fozia Qazi to enlighten us with her talk on the language of universe. Uh, Over to you, ma'am.
Thank you. I'm delighted to be joining you all for this. Normally, it is a one-on-one sort of offline session, which I prefer normally because it's more interactive. I get to see the participants, talk to them individually as well. Also, because it allows the participants to also sort of interact a little bit more than this. But the advantage, I guess, of the online mode is that I don't have to go out in the snow. So I'm happy to be here. I've given the audience, and I was told it's a sort of course on sciences, so which means all of you would have a science background. I just like to have a sense of the audience. If you could sort of tell me what your field is, which branch of science, just a rough idea to get a sense of the audience.
Yeah, ma'am. We have participants from physical sciences, mathematical sciences, chemical sciences, biological sciences. Almost all are from science background, because this is the
Okay.
research, this refresher course on science.
On sciences. So there is somebody from math or statistics also?
Yeah, ma'am. Myself, the moderator of this session is from mathematics. I am actually assistant professor, Department of Mathematics, South Campus, University of Kashmir.
Okay. Well, good to have some mathematicians, but I've sort of tailored my talk for the general audience, and I will be talking about mathematics, but what you will see is there will not be a single formula or an equation in my entire presentation. The idea is to just give you a general sense of how mathematics, to some sense, how it evolved, and also how it is used in some, sciences as well as non-science applications. Yes, somebody said something?
Yes, actually, there is one of the participants, Dr. Bablu Samanta. He also belongs to mathematics, and he has joined all the way from Western Midnapur, West Bengal.
Oh, wow, wonderful. Welcome. But without the snow. So he's missing all the snow. So let me start the PowerPoint. I'll do a screen share and then. Can you see my the title slide?
Yeah, it's coming, about to come.
Okay. Let me know when you see it.
Yeah, it's preparing to come. You have started sharing the screen, taking a little bit more time.
Let me see.
Yeah, now
Okay, so now it shows. Is it visible?
Yeah, ma'am, it's visible.
Okay. So I've titled the language of the universe, and because of the quote I'm starting with, this is a quote from Galileo. The universe cannot be read until we have learned the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometric figures, without which it is humanly impossible to comprehend a single word. This is Galileo, and because of his quote, many other people sort of started writing or thinking of mathematics as the language of the universe. Now, I want to say that by calling it the language of the universe, I'm not, number one, saying that mathematics has all the answers. It doesn't. Any human endeavor can never sort of claim to have all the answers. So it's not going to answer questions like, on existence of God or something. But what mathematics does is that it is very efficient at explaining our physical world. And that's what the observation has been over years and centuries, that we're able to explain many of the natural phenomena through the language of mathematics. And in many ways, the language of mathematics itself evolved because of trying to explain some of those phenomena. So I'll just show you some pictures which you've all seen. And as Galileo was talking about triangles and circles being the letters of the language of mathematics, we see circles and triangles and squares and all these other shapes all around us. This is a drop of water that has fallen on a sort of a still surface of water. It makes circles. As children, we all, at one point or another, threw pebbles in water and were fascinated by how those circles were formed. You can see flowers that have the shape of triangles or pentagons. The picture on the right side is that of a mint plant. It's the stem of a mint. And the distinctive feature of the mint plant is that if you look at the stem, it's not round. So it's actually square shaped. So if you take a cross section of it, it would be a square rather than a circle. So we see things around us and we see certain mathematical shapes. We had a lot of snow here for the last 4 or 5 days. And if you observe a snowflake very closely, it has a very beautiful shape. There are symmetries in it. This one is almost like a hexagon, but it's also a fractal. And we'll talk about that a little bit later. And some of you may know this already, that snowflakes are all different from each other. Every individual snowflake is distinct from any other snowflake, which is a remarkable property. You would also have seen this. If you look at a honeycomb, the individual cells of the honeycomb have a hexagonal shape. And it is related to what is known as tiling in mathematics. Again, we'll come back to this picture a little later. Does this look familiar to people? We often think of pine cones and sunflower sort of seed heads. When we see them, we think of Fibonacci sequence. I don't know how many of you are familiar with Fibonacci sequence. Let me try and see where I can get the, yeah, there we go. Fibonacci sequence is essentially a sequence of numbers where you start with a pair of ones and then you add those two to get the next number. So 1 plus 1 is 2. Then you would add 2 plus 1 would be 3. Then 3 plus 2 would be 5. 5 plus 3 would be 8, and so on. 13, 21, and then you keep going. So that's Fibonacci sequence, named after a mathematician called Fibonacci. This sequence occurs quite often in nature. So if you, next time you go to Pahalgam or Gulmarg or any of these areas and you pick up a pine cone, look at the bottom of the pine cone and there will be these spirals. This picture has the spirals marked clockwise as well as counterclockwise. And the number of spirals will be Fibonacci numbers, consecutive. So in this case, the picture that you have here, you have 8 and 13 spirals. So which are, again, consecutive Fibonacci numbers. Many of the pine cones that I've observed in Kashmir, because I got this picture from the net, but in Kashmir, more often than not, you will see 5 and 8 as the number of spirals. So in one direction, 5, which is clockwise, and counterclockwise, it will be 8. You can also see Fibonacci numbers in the seed heads of many flowers, in this case, sunflower. It's 34 and one of the higher numbers. So it occurs in nature quite a bit, also in terms of how leaves are formed on a stem. So this shell is called the nautilus shell. And if you look at the spiral, this spiral is a close approximation of something called the golden spiral, which arises from another number, which is called golden ratio, which is closely related also to Fibonacci sequence. This is an actual shell, and the spiral is a very good fit for the golden spiral. So these mathematical concepts occur in nature quite a bit. And I often like to quote this saying from HRD, who was a British mathematician and number theorist. You may have heard his name in connection with Ramanujan. He's the one who sort of took Ramanujan under his wing and brought him to Cambridge. He says a mathematician, like a painter or a poet, is a maker of patterns. If his patterns are more permanent than theirs, it's because they're made with ideas. So mathematics is, we often call it the study of patterns. I mean, this is one way of looking at it. And nature itself, you see many patterns. One of the earliest patterns that humans had observed was the planetary motion. As we all know, the planets move in an elliptical orbit. An ellipse is one of the shapes studied in mathematics. If you throw a stone in the air, its path would be that of a parabola. This is also, I mean, studied very early on in schools and in calculus. We have Fibonacci sequence, we just talked about it. We have fractals in nature, which have patterns, the snowflake being one of the examples. And crystals, and again, we'll talk about this again after a few slides. Crystals also have a certain structure and certain pattern to them, which is closely connected to mathematics also. So how did mathematics evolve? We have a tendency, if you ask somebody on the street, they would often talk about mathematics being this, abstract discipline that people do, or mathematicians do mathematics just for the sake of it. That there are no real world applications to mathematics. It's not very relevant to our day-to-day lives. Sometimes students who are studying things like algebra or calculus will ask you, where will I ever need this in real life? So the notion that exists about mathematics is that people do it for its own sake, for the sake of doing mathematics, that it's this abstract, esoteric discipline that doesn't really have relevance in our day-to-day lives. But you're all scientists. You know better than the person, sort of the random person on the street. In sciences, how mathematics is used and how much is used in sciences. So the reality is that mathematics evolved because there was a practical need that it had to address. And I'll give examples about it. But if we think about the basic simple counting that we do, the earliest examples of counting or some sort of sense of counting comes from almost 40,000 years ago, where we've discovered that there were notches made on bones or made on stones. And these notches were meant to represent some number. So whether this was to count the number of animals they had, or whether this was to count the number of days, sort of some attempt at a calendar, we don't know, but it was an attempt at counting, and 40,000 years ago. And then as humans progressed, and they needed additional sort of information in terms of quantities, in terms of study of shapes, in terms of measuring things. When human civilization started to settle down and became agrarian, they had to measure land. They had to be able to figure out the area of certain shapes. They had to be able to do simple calculations, or later on more complex calculations. And that gave rise to number systems. It gave rise to geometry when we do measurements and when we do study of shapes. Calculations eventually led to algebra, where we could then simplify. And when we observe natural patterns, it also led to other mathematical ideas. And the abstract nature of it and the complexity of mathematics, that came later. If you think about the simple task of counting, the early humans could distinguish, for example, they could distinguish between 2 cows and 7 cows, or 2 cows and 5 cows. Because this is a basic notion where they are able to count a particular quantity. But the notion of the number 2, that if I have 2 apples and 2 cows, there is a similarity there. That notion is more abstract, and that came much later. Sort of understanding the 2 as a number. That's a very abstract notion. That came later, but being able to count 2 quantities or 10 quantities, which was more practical, is a sort of a very early achievement. The other aspect of mathematics, and this is what is beautiful about it also, is the longevity. That there may be a mathematical formula which is 3,000 years old or 1,000 years old, and it is just as true today as it was 1,000 years ago or 2,000 years ago. You know, area of a circle was pi r square at the time of the Greeks, and it is pi r square even now. It hasn't changed. We haven't sort of modified our theory. So that is what is beautiful about many of the mathematical ideas.
We're not able to hear you, ma'am. Can you hear me, Dr. Fawzia Qazi?
So it's perhaps problem for her side.
Yeah, it seems Dr. Fawzia Qazi has got disconnected. I'll try to call her. Yes, I have spoken to her. She is trying to connect back. She has got disconnected in between.
Okay, sir.
Khurshid Saab, we have to unmute her the moment she joins. Please take care. Dr. Feroz Saab, who
Yes, sir.
in case we get time
Yes, sir.
in this session, Dr. Muhammad Muslim is ready to present.
Okay, sir.
We invite Dr. Muhammad Muslim in case we get time after Madam Fawzia Qazi's presentation.
Okay, sir.
May I know who else is ready to present today? Is there anybody else who can present today? Yeah, Dr. Fawzia Qazi has just texted me. She is restarting the connection. There was some issue with the broadband. Yes, she has joined back. Please unmute yourself, ma'am. Dr. Fawzia Qazi, yes, you have unmuted. I'm asking you again to unmute, ma'am, please.
I had unmuted, but it must not have.
Yes, something
Can you
went
hear
wrong.
me?
Yes, we can hear you. Please go ahead. Share your
Okay. Where you lost me? This slide?
your slides are not yet visible, ma'am, though you are, yes. I think, yes, this was the one. Dr. Feroz, was this the one?
Yes, sir.
Okay. So what I was saying is that the way that mathematics evolved is that there was a practical need that gave rise to a particular type of mathematics, whether it was counting or geometry, where you do calculations, algebra. The abstract part of it came later. But there are also cultures which are not very advanced in terms of how we think of advanced cultures, where there's very little development of mathematics. And the example is Peraha tribe which consists of about 700-800 people total. It's a very remote, very isolated tribe, or had been isolated for a long time. They don't have a number system. They don't have words, for example, for the number 1. They don't have a word for 2. They don't have a word for 3. They can't even think beyond 3. The only 3 words that come close to being quote unquote numbers are they have one word which denotes a small quantity. They have another word which is for somewhat large quantity. And they have a third word which is for many. That's it. And it's a good example that if the society is not settled in terms of agriculture and trade and so on, there's no need for number systems. There's no need for any complex mathematics. And these people haven't found a need. That's how isolated they have been, and that's how simple their lifestyle is. So there is a need for a formal number system, or very little need if there is no settled agriculture or trade. So just to talk about a few number systems that evolved over a period of time. We've had Chinese, they had something called the rod numerals. We have Babylonians, 3, 4, 5,000 years ago, they had a base 60 number system. Egyptians had it, Mayans had it. Interesting case is of Incas who didn't have a written language at all, but they had a number system where they could record numbers and do calculations. And the way they did that is they would tie knots on threads. And the position of the thread was like, if you had, for example, 325, you would have a thread with 3 knots in it, then a thread with 2 knots in it, and then a thread with 5 knots in it. And that indicated the number 325 without a written language, as I said. So these khipus have been discovered and are a good sort of shed light on how they did their calculations. In Europe, the number system that was used is the Roman number system. Most of you would be familiar with it, the Roman numerals, which are very difficult to manipulate. For example, if I were to write, I'll write it here, say I have XXX, this is a Roman number. X is for 10 and the 1. If I were to multiply it by, let's say, we'll do another one. This means 42. So I have to, if you're multiplying, this is multiplication. If you had to multiply it, it's very difficult because for us, for example, we would be trying to convert the first one to 34 and the second one to 42, and then we would use our normal methods for multiplying. But Romans didn't have that, and multiplication and division using this number system was actually taught in the universities. So there was a very elite, very small number of people who could actually manipulate these numbers and use them for calculations and so on. Which is why the decimal number system, which is often called the Hindu-Arabic decimal system, became very popular. And this is the most efficient of all the number systems so far. And it became popular because shopkeepers and accountants needed to do quick calculations. So it was a number system that the general public could use. It wasn't restricted to university educated people. And that's how it became very popular. So there was a very practical need for this number system to evolve the way it evolved. Which again points to that mathematics has traditionally developed and evolved because there was always some practical need for that kind of mathematics. And if you look at the number system, and since I'm talking about applications, I thought I'd put one application that went wrong, in the sense that the example is of NASA losing an orbiter. This was in 1999, so not that long ago. They had instructed the craft in imperial units. In the US, inches and feet are used instead of the metric. The orbiter was basically programmed for metric units. So when they put in the inches and feet, the imperial units, it went off course and burned up. And it was $100 million loss simply because the units were wrong. Instead of metric, they put in imperial units. So a small change in the number can cause a big loss. Switching to geometry, it has evolved from understanding, obviously, basic shapes. At the beginning to now, we use very sophisticated computer graphics, art, architecture, material culture. They all benefit from very basic fundamental ideas of geometry. In Kashmir, for example, we are very familiar with khatamban ceilings or with lattice windows. They all use geometry. Carpenters use geometry quite a bit. And there is a branch of mathematics which is called topology, which also originated sort of from geometry, but it studies geometric objects subjected to continuous transformations, which basically means I can stretch, twist, bend, or shrink the object, and I want to see what happens to the object when I do that. I'm not allowed to cut or glue or punch a hole, that sort of thing. So basically just continuous transformations. Cutting or gluing would not be continuous in this case. So this branch is quite interesting. You have, if you've ever heard of Mobius band or Klein bottle, it comes from this branch of mathematics. And within topology, there is a sort of a subset called knot theory. And the story of this is quite interesting. It was, knot theory sort of came into being in late 19th century when somebody sort of proposed a theory on how the atoms were made. And they were basically saying that atoms were made of ether and ether was made of knots. So suddenly everybody got interested in knots, all the scientists. But then with modern atomic theory, the first theory was negated. So all the scientists that were interested lost interest in knots. But mathematicians continued to study knots. And as I said, it's a branch of mathematics within topology that is studied even now. And what was interesting is that 30, 40 years later, or in this case, almost 100 years later, it was a mathematician who solved a problem on molecular biology connected to DNA. So the issue was, what would the action of the enzyme be on the DNA strand? And he showed that there are only certain types of knots that can arise. And this is an example of sort of a kind of endeavor, mathematical endeavor that everybody would have said is very abstract and very useless or very esoteric. And suddenly it has a very useful application in a field which you wouldn't necessarily imagine right away. So knot theory is, I mean, obviously used these days for DNA understanding also. The other notion that I want to talk about is symmetry. And this picture that you see here is a very old Egyptian, ancient Egyptian pattern. It's the type of pattern you would see nowadays in a rug, carpet, or wallpaper, that sort of thing. But this is a very old pattern, and it's not unique to Egypt. We have had these kinds of patterns. They are called periodic patterns or tilings. And it was a mathematician by the name of Andreas Speiser, who was a group theorist, another branch of mathematics. He called this a mathematical achievement of the first rank. When we think of mathematics, we tend to think of formulas, we tend to think of equations, numbers, geometry. Those are the mathematical achievements, so to speak. We don't think of patterns, design, a drawing. But it turns out that if you want to understand these types of patterns or symmetries, you have to use the language of mathematics. So mathematically, we define symmetries, what we call rigid symmetries, we put them into 4 categories. So translation, reflection, rotation, and glide reflection. So translation is where you simply move the pattern, a fixed distance. Reflection, we're all familiar with. It's often also called bilateral symmetry. It's the symmetry that you see very often in nature. You look at a human face, there is a bilateral symmetry in it. Our left side is more or less same or a reflection of the right side, unless you have a crooked nose or something. Generally speaking, one side is a reflection of the other. Animals have the same bilateral symmetry. If an animal had, like, for example, right leg was longer than left leg, you wouldn't be able to walk very well. So there is a need for this kind of symmetry also. Rotational symmetry is also quite common in nature. If you look at a flower, which has, say, 4 or 5 petals, you'll be able to rotate it 4 or 5 times and get back to the original. Glide reflection is simply like, we've had snow for the past several days. If you walked in the snow and you look at your footsteps in the snow, that's an example of glide reflection. It's basically reflection where you have translated the image. So if you think of your left foot as a reflection of your right foot, then you're just pushing the right foot forward, it becomes glide reflection. So these are the 4 rigid symmetries. And then the 5th one is something called symmetry of scale, or also what is known as self-similarity, which we see in fractals, that if you zoom into a portion of the pattern, it looks exactly like the original, and snowflakes have that property also, all fractals. So the language to explain the symmetry and various properties of it, mathematics evolved to explain that, and it's a branch of mathematics called group theory, where you classify these patterns, like the Egyptian one we saw earlier. These are known as periodic patterns. You classify them according to their symmetry groups. So it's a classification that essentially tells us what kind of symmetries are present in that pattern. We saw there are 4 symmetries for the periodic patterns, but you can have combinations of those 4. So what arises out of those combinations, we then classify that as per the symmetry group. So what are the applications of symmetry groups? They describe the atomic structure of crystals. So the chemists in the audience would understand that. And the periodic structure of these is described by periodic tilings, like the pattern you saw earlier. But there are also, when I talked about symmetry of scale, or what is the self-similarity, which is non-periodic patterns or tilings, but they have symmetry of scale. And this was discovered in the 20th century. They're often called Penrose tilings. And it turns out that even these non-periodic tilings, which have symmetry of scale, can describe the structure of something called quasi-crystals. And quasi-crystals were discovered again in nature. It was quite a big discovery that this is not something very theoretical. They are found in nature also. I think the first quasi-crystal that was discovered has a very mathematical name. It's called icosahedrite, if I remember correctly. Icosahedron is a term used in mathematics for one of the regular solids. And so it was named after that, icosahedrite. It does occur in nature, but it doesn't have the crystalline structure, which is very periodic. This one is non-periodic. And I'll just show you a couple of pictures of the Penrose tiling. Quasi-crystals, it turns out, are also used in making non-stick frying pans. I mean, who would have thought? You have some very esoteric mathematical idea ended up on a non-stick frying pan. This is a Penrose tiling. Roger Penrose was a physicist who first figured this out. He's not the first one to have come up with a non-periodic tiling with symmetry of scale. There were other mathematicians before him, but the number of tiles they used were, I mean, it was a theoretical proof, which required thousands of tiles. But Penrose was the one who narrowed it down to originally 5 tiles. And then from 5, he narrowed it down further to 2 tiles. And this is the pattern with 2 tiles, 2 kinds of rhombi. And this is Roger Penrose standing on top of Penrose tiling. The floor that you see there is actually Penrose tiling with 2 types of tiles. Both are rhombi, the white one and the dark one. One is fat rhombus and the other one is thin rhombus. Now, coming to tiles, again, we have, when we say tiling, we mean that you're covering the plane with some shapes without leaving any gaps.
Ma'am, you are not audible here.
I think she has again lost the connection. Dr. Fozia Kazi, ma'am, are you able to hear me? Your screen is visible. Dr. Fozia Kazi, can you hear me? Dr. Fozia, am I audible to you?
Oh, apologies for the bad connection. I don't know what happened. It was fine until about an hour ago. Let me go back to the slide. Is this where we stopped?
Yeah, it's not visible.
Can you see the slide?
No, ma'am, it's not visible yet.
Okay, let me try again. I think I may have to restart it. Can you see it now?
No, it's starting, ma'am. It may take a minute.
Let me know when you see it.
Okay, ma'am.
Can you see it?
Yeah, ma'am.
Okay.
But
Is this where I was? Because
no,
I don't know where.
no, ma'am. I
lost
think
the
I think you have forwarded the slides.
Did you see this one?
Yeah. This we have seen.
The
This
cat.
no, ma'am. This one
And
not
this? Huh?
We were actually on the topic that was actually tiling on the plane.
Okay. This one.
Yes, tiling of the plane.
Yeah. Okay. So 3 types of regular polygons can tile the plane. Tiling means you can cover the plane without leaving any gaps. This is sort of an informal definition of tiling. And these are the only 3 that can tile the plane. So coming from tiling, I'm showing a picture of a cat in snow. The reason is that when it is cold, we tend to curl up. We try to, and curling up means we try to convert ourselves into a ball, so to speak. Dogs often do that. Cats do that when they're cold. So why do we do that? The second question is, if you blow a soap bubble, it's always spherical. Why is that? And the third question is back to the honeycomb. Why is the shape of the honeycomb hexagonal? And the answer to all 3 of those questions lies in a mathematical theorem called isoperimetric theorem. So I'll give you sort of a
I think Dr. Fauzia has got disconnected again. Dr. Feroz, can you hear me?
Yeah, sir, I am hearing.
I keep disconnecting for some reason. So let me. Can someone tell me when they start seeing the screen?
Yeah, ma'am, it's honeycomb conjecture, but you were actually on the slide where it was discussing isoperimetric theorem.
Okay. Did I finish that or no?
No. This one actually.
Okay, so what I was explaining is that what is the isoperimetric theorem? If I have all these different shapes in the plane, triangle, square, rectangle, circle, any random shape, and all of them have the same area, then circle is the one that will have the smallest perimeter. Similarly, in the three-dimensional space, instead of triangle or square, if I take, for example, cones or cylinders or any solid, random solid, all of them have the same volume, then the sphere will have the least surface area. And it has a dual, it can work the other way also. If you start with a fixed surface area, then the maximum volume will be the sphere. So it is the isoperimetric theorem that makes us curl up into a ball when we are feeling cold, because when we make ourselves into as close to a ball as possible, our surface area is minimized. And therefore the exposure to cold, the area that is exposed to cold is minimized, which is why we do it. This is why dogs and cats and other animals do it also. Then we come to the honeycomb conjecture. The idea when bees are making the honeycomb, they would want to minimize labor. it takes a lot of effort to gather the wax and then build the honeycomb. So intuitively, the idea is to simplify the process, but use minimum amount of wax. But at the same time, have a design that will allow you to have the maximum amount of honey. So the honey becomes the volume, and the shape of the cells is related to the surface area. Now, isoperimetric theorem tells us that surface area, if you take a simple soap bubble, why is it spherical? It's because of the isoperimetric theorem. The air inside the soap bubble is a fixed volume, and so the shape becomes spherical because that has the minimum surface area. But this is not just one circle or one sphere, it is a combination. So if I were to try and have a shape which is try and do a tiling with the, I can't seem to write on this, with the circles. If I do this, or try to do a tiling with circles, I will leave gaps. So instead of circles, we go back to our hexagonal tiling, which is where you had these hexagons, and they tile the plane nicely without leaving any gaps. So instead of circles, it's either hexagons, or I could use, or the bees could be using square type cells, or they could be using the triangular. These were the three options that we had in terms of tiling the plane. And the honeycomb conjecture was basically that you get the minimal perimeter from the hexagons, because hexagons are the ones which are closest to a circle out of these three. And it was again proven in the 20th century only that it is indeed the hexagons that give us the minimal perimeter. So it looks like the bees are also trying to, just like the cats and dogs, the bees are also trying to minimize the perimeter in this case, or the surface area if you look at the entire cell. And the way the bees do this is their bodies are round in shape. So when they start making the cells, the cell itself starts out as circular in shape. And then the cells are heated, and the conjecture is that they heat there are a couple of conjectures as to exactly how they do it. But once the wax starts to melt a little, it will automatically then take the hexagonal shape, which is on the right side of this picture, because that is the optimal shape for this. And what is nice about this is then you can also, when you look at the soap bubbles aspect of it, and you think of, okay, one soap bubble is a ball in shape or spherical in shape. But what happens if we combine two soap bubbles? We still want the optimal surface area. And it was shown that the way you can combine the soap bubbles is when the angles, wherever they meet, the angles have to be 120 each. Same thing for the when three soap bubbles meet. But if it's four or more, this is still, the conjecture is that it will still be 120 angle, but it hasn't mathematically been proven yet. The first two have been proven. So if you look at the bottom right-hand picture, when you have the 120 angle, for example, here, you have 120, 120. It's beginning to look more and more like a hexagon because hexagons, the angles are 120. So if you combine a lot of soap bubbles together, this is a picture of foam, basically. next time you take a bath or you are washing some clothes, look at the soap bubbles, and this is what they look like when they have combined. And you will notice they are more or less like hexagons, not quite, it's like the honeycomb, the edges, because this is not a very stable structure the way a honeycomb is. But it is, if the conditions were ideal, then these would also have the same structure, hexagonal structure, because that gives us the optimal surface area. This is where I'll stop with the good news that the first woman to win the Abel Prize, this is another very famous prize in mathematics, and the first woman won it only a couple of years ago, was Karen Uhlenbeck, and she had done some pioneering work on soap bubbles. So studying soap bubbles is good. And this is where I'll stop. Thank you.
Thank you, ma'am.
Dr. Feroz, you can take some of the questions from the chat box.
Yes, sir. Thank you, ma'am, for this nice presentation on the language of the universe. Ma'am, we have certain questions in the chat box from the participants. The first question is from Dr. Shaukat Ganai. He's asking what kind of properties knot theory tells us about the enzyme that unknot DNA molecule.
I don't see it here. What is the question again?
Yes, ma'am. It's what kind of properties knot theory tells us about the enzyme that unknot DNA molecule.
I mean, I am not very familiar with knot theory, but basically what it does is that when you combine DNA molecule or replicate DNA molecule, what happens to the strands? The strands are very knotted, sort of very tangled structures. And it's sort of physically impossible to check what will happen. And knot theory looks at the structure of the knot and then tells you what possible knots can arise if you have this enzyme action. This is what basically mathematics can help the biologist with. Theoretically, tell you that these are the knots possible and these ones are not possible.
Thank you, ma'am. Ma'am, we have one more question from Dr. Sayar Ahmed. He's asking, how can we develop mathematical temper among students?
It's a very good question, and it's one very close to my heart because it sort of pains me to see that very bright students come even to our university. I come across them at other universities also, who are very bright and who have a sort of mind which is good for mathematics, but they are lost to mathematics because the way it is taught in schools is very sort of formula centric. It's very algorithm centric, that you are taught this is the method, you replicate or regurgitate that method. And we tend not to allow them to imagine or be creative in a mathematics class. I think that's one of the tragedies that mathematics education in general, we tend to be very test centric. We tend to be very sort of follow the procedure in everything. And mathematics is not about following procedures. It's more about creativity. Formulas and equations come later on, but the idea needs to be communicated first before you get bogged down with procedures and formulas. So the answer is teach it a little differently or have activities outside of classrooms, which, I mean, we do it at my university. We have a program called Impact, and we have had math festivals, we have had workshops where we don't do formula-centric mathematics. We give them activities where they do soap bubbles, for example. It's fun. They can do calculate, approximate pi. They do topology with, you know, you tie them in ropes and then they have to figure out how to untie themselves. Yeah, it's all topology, and then all other like math and art and all of these other branches of mathematics come together. It's fun. It gets them interested, and without using any of the computational things that often scare them.
Exactly, ma'am. There's one more question from Dr. Tariq Makbul. I think you have answered the question. He's saying, rightly said, mathematics is the language of universe, but unfortunately not universally understand. Your thoughts?
Yeah, the whole point of this presentation was exactly to address that issue.
Yes, ma'am. There's one more question from Dr. S.M. Zubair. Ma'am, you said Piraha tribe from Amazonian forests in Brazil don't have words for numerals. Who else from this part of the world are still in? Sorry, ma'am.
There aren't many. No, I saw the question. There aren't many cultures or tribes which are anumeric. The term that's used is anumeric, that they don't have words for numbers. Piraha is one of the few. And as I said, they're only like 700 or 800 in number. In our part of the world, there, as far as I know, there aren't any. It is that if you look at, because Piraha is the tribe that has been studied, people have tried to study what mathematical literacy they have. I mean, can they do computations? There was some controversy early on as to, I mean, there were two studies done and got two different results. And it turned out that the group that had been part of the study, somebody had already taught them numbers. So they gave obviously different answers than the earlier group. But it has been found that they can do, you know, one-to-one correspondence. Is everybody familiar with it? I can, for example, if I have to prove that my left hand has the same number of fingers as my right hand, all I have to do is put my two hands together and match the fingers. So my thumb on the right side matches the thumb on the left hand, similarly the four fingers and so on. It's a one-to-one match. Counting is all about one-to-one correspondence. When I count things and I say, suppose I have three things on the table and I say 1, 2, 3, I am doing a one-to-one correspondence. The first object I'm matching with the number or the word 1. The second object I'm matching with the word 2, and the third object with the word 3. It's a matching, one-to-one matching. The Piraha could not do the one-to-one matching if the number was more than 3. They could do, if you put, say, two objects on the table and you tell them to put two other or, you know, some other objects and match, they could do up to 2 or 3, but not beyond. The reason is that their culture is, their society is so simple that there was no need to count. That's basically the bottom line. They were so isolated that their word for other languages, you know, they have their own language, but their word for other languages translates to something like, you could say bakwas, you know, that everything outside their universe or that small tribe, they were not interested in, because they were so isolated that all the other languages are for them uninteresting. So that sort of tells you that their need for mathematics was very minimal. So which is why they have only 3 words which come close to like small, large, and many. Sometimes it is written as 1, 2, and many. Does that answer? It's not that they're reluctant to learn, it's just that there's no need for them. If you teach them now, they will learn, but there is no requirement, there's no need in their culture to do any calculations, to count large number of things. So there's no development of mathematics for that reason.
Dr. Syed Mir wants to ask a question. Please go ahead.
Am I audible, sir?
Yes,
Sir,
yes,
you are
go
not
ahead.
allowed. Unmute me, please.
I have
We can
unmuted.
hear you. We can hear you.
Okay, okay. Thank you, ma'am, for the next very beautiful lecture. I want to share an observation, sort of a question or an observation. Have the languages of the regions and the like language of the numericals, you said, like numbering co-evolved? Like what I was observing was, for example, we have the numbering in Arabic is Wahid Isna Salasa Arba, while as in Kashmir we have Agz Triyat Zur, which I found is very similar to, for example, numerical numbering like in Germany, ein, zwei, drei, and our 3 with respect to Arabic. I mean, why have these things co-evolved with the language, or our numbering has come much earlier than that?
The words themselves are different. I mean, that's a linguistic question. But in terms of the symbols and how we write mathematics, there is a connection. In terms of, say, the word for something like drei, sei, eins in German, is it similar to ours? There's a linguistic question. I'm not a linguist. But if you look at how we write numbers, let me just do a whiteboard. It doesn't allow whiteboard, does it? I can't do a whiteboard on this. Is there a way to get whiteboard here? I can't see it.
Ma'am, we have IT support staff here. Sohail Saab, are you there? Khurshid Saab?
Because normally you get it in the screen share, but I don't see it here.
That annotation, we have to put on the annotation.
Where is? I don't see it on my screen.
Khurshid Saab, please put on the annotation. Just a minute, I'll try to see if it is available here. Khurshid Saab, can we activate the annotation tool?
Let me try to do the screen share with because I could write on.
Yeah, earlier you were just.
No, that was the PowerPoint. Yeah. So let me see if I can do it here. See, when we write numbers, say I'll write to 234. It has 4 units, right? 3 tens and 2 hundreds. The units come first, then tens, and then hundreds. When we write even whether we're writing it in Kashmir or whether we're writing it in America, the numbers are written the same way. But the question is, if I were writing in, say, in America, I would write English, which is written from left to right. So we go in this direction. But if you look at the number, we're essentially going from right to left. The unit is here on the extreme right, and then this, and then this. Question is, why is that? And the reason is that because the number system that we use is what I had written earlier, the Hindu-Arabic number system. And it was Khwarizmi who gave it shape. He used the Indian numerals which had been used before him, but gave it shape, made it a proper systematic entity. And then after Khwarizmi, there were other mathematicians in the Islamic world who then extended this number system to the decimals. But the fact is that because Arabic is written from right to left, we inherited that way of sort of writing, that the unit comes to we write it from left to right, but the unit, which is the first number, which should be the first number, is on the extreme right. So there is a similarity or connection between how numbers evolved. The decimal system came to Europe through Fibonacci, actually, who had learned it from merchants in North Africa. And these were Muslim merchants in Algeria. I think his father was a diplomat at the time in Algeria. So he spent a lot of time in Algeria. He learned the decimal number system, which was at that time very popular all across the Muslim world. And then he brought it to Europe. So when the numbers were written in Europe, it was basically adopting the way they were written in Arabic. Although the symbols are different. I mean, in Arabic, you would write things like this, right? 3 and then 4 is like this. So different symbols, but the same number. Any other question?
No, I think Dr. Feroz, we don't have any more questions, so you may please conclude the session.
No, ma'am, we don't have any question now in the chat box.
There was one question, excuse me.
Yes,
Please, please find it in the chat box, please.
You can go ahead and ask straight away.
It is something, apart from maths, as ma'am has been in US. Now I want to know, it is not now a hidden fact that people from this subcontinent are more hardworking than the people of West. So what makes us, why we are lagging behind still?
I wouldn't necessarily, I mean, it's a very big generalization to say that people from one area are more hardworking than people from another area. People are the same more or less everywhere. If you give them a good system, they work hard. If you give them a good system, they're more efficient. And I think the reason why a lot of the scientific development happens in the West is because of the system being more efficient, there being more accountability, and that helps. If you look at history and history of science, it has always been the case that science evolves and develops when there is support given to scientists and scholars and philosophers. That support is often monetary support. In old times, it was a king or a ruler who provided the financial support to the scientists. I mean, we have examples in our own history also. Nowadays, it is the grants that these agencies like UGC over here do. But it is a question of finances. It is a question of efficiency in terms of the system you have developed. And that's always, if the conditions are right, no matter which part of the world you're in, there will be good scientific progress. I mean, that's given. Many of our people, when they go to countries in the Western world, they do wonderfully well because they have the resources available to them that they may not over here.
thank you, ma'am. I think We don't have any other question. Any other question from the participants, please? Okay, there's no response now. Ma'am, we are really thankful of you for this very fascinating lecture on the language of the universe. In this lecture, you have discussed many things. You have mentioned the existence of mathematics, already existence of mathematics in the nature, so many concepts in the beautiful figures like the golden ratio, the fractal geometry, Fibonacci sequence, and many other concepts are already existing in the beauty of the nature. You already you have you also mentioned the evolution of mathematics. What was the need of the hour for the evolution of mathematics? I can say the way you presented the talk, you have not only discussed the language of the universe. In this talk, you have already also incorporated the uh, history of mathematics, the applications of mathematics, primarily how mathematics were used in the fields. You have also you also discussed the future applications of mathematics. So we are very much thankful of you. We hope you will be also available in the future programs conducted by UGC HRDC University of Kashmir. So on behalf of the participants and the UGC HRDC team of University of Kashmir, I thank you for this very nice presentation. Thank you.
Thank you all. Whenever I give a presentation, I am always keen to see what kind of questions the audience asks, because that tells me whether they were interested in the talk or not. And I was happy to see that I got some very good questions. Thank you all.
Thank you.
Thank you once again.
And good luck with the rest of the workshop.
Thank you. Dr. Feroz, I think you can go ahead and invite Dr. Muhammad Muslim for his participant presentation. We can have one participant presentation at least, I think. Then we'll close.
Exactly, sir.
I'll unmute Dr. Muhammad Muslim. Give me a second, please.
Now, to continue the session, we request the next presenter. Who's the next?
Dr. Muhammad Muslim.
Yes, Dr. Muhammad Muslim. Please present your topic.
Okay, am I audible?
Yeah.
Yeah. Dr. Greed, coordinator UGC, and our moderator for the session, Dr. Feroz, and fellow participants. Assalamu alaikum wa rahmatullah. So I'll be briefly presenting about climatic extremities and understanding them through the observation and the modeling studies. So this is the contents of my presentation. A brief overview of the climatic extremities. I'll give an historical perspective of the understanding climatic extremities over the Kashmir region, and I'll be sharing it with you, the modeling results of the study conducted by my research team. So far as the climatic extremities are concerned, IPCC, that's Intergovernmental Panel on the Climate Change, defined them as the extreme events of the meteorological conditions as an event that are rare in the statistical reference distribution at a particular place. If we see climatic extremities, they are natural within the natural variability of a climate change, and over the years, due to anthropogenic influences, these climatic extremities have evolved. And extreme event definition depends upon the local reference. Say, for example, a snowfall in a Gulmarg with a 7.5 feet snowfall can be considered an extremity in Kashmir Valley, whereas at the higher altitude, it is considered to be the normal. These climate extremities and the climate patterns are among one of the serious challenges that the climatic change is posing over the years. World Meteorological Organization, WMO, recommends 27 climatic extremities as a climate change monitoring indices, and they are further divided into 16 extreme temperature indices and 11 precipitation indices. So far as the past climatic extremities over the Kashmir region have been concerned, have been mapped, we have been observing them with respect to the anomalies with respect to the temperature and the precipitation patterns. And most of the recorded data about these climatic extremities have been seen with respect to the extremities of precipitation data. And there is a published data that's published annually in the annual climate summaries published by the Intermeteorological Department, Pune. So these are the extremities, over the past 50 years, over the various stations of Kashmir. If you see Srinagar, we have had a extremity around 29 December 1990. Just to emphasize here that it's a data from 1951 to 2010, not beyond that. So similarly, we have the extremities with respect to the Pulwama, the two stations of the Pulwama. Some of you may be, having a question that, okay, there are only 6 MET stations, but I'm presenting the data for a large stations over here. Basically, we have the 6 complete meteorological stations that record both the precipitation and the temperature, while the rest, there are many gauge stations that are in collaboration with the IFC, Irrigation and Flood Control, whereby we measure the rainfall station. And most of the data, extremity data, have been understood with respect to those stations. So similarly, likewise, we have it for Kopwara, we have Kulgam, then we have the extreme climatic, conditions that have occurred. Our Gandarbal, even though we don't have any stations, but we have a large rainfall gauging stations in the Gandarbal. Similarly, Shopian, and then we have for Baramulla and Bandipora likewise. And then Badgam, we have had like 174, and we say these basically, how do we classify these extremities is like we see their annual precipitation behavior. Say, for example, we'll consider if we have an annual rainfall of 1200 mm in Srinagar city, it is considered to be an extremity for a Srinagar, because our annual, on an average, if you say rainfall behavior for a climate normal, it's almost about 680 to 700 millimeter. That's how we understand this extreme behavior over a particular station. Similarly, on the same basis, we have been calculating the extremities in terms of the climatic drought. Okay, this is not the agricultural drought, this is meteorological drought, basically, whereby we have had 50% less amount of a rainfall over the various districts. And this is the record over the various districts about the extremities with respect to the climatic drought. And similarly, we have the excessive rainfall, and as I earlier said, that these excessive rainfall are basically calculated on the basis of an average threshold. Say, for example, Srinagar, as I gave an example, like we have a 700 mm of rainfall. If we get a rainfall above 700 mm, we'll classify the rainfall, and on the basis of these, we characterize and years with the excessive rainfall and the years with the successive excessive rainfall, and even the drought years. So far as the modeling study of these extremities are concerned, we do tend to calculate these on the basis of a set of equation that is used to compute all the 27 indices referred by WHO as the core climate indices. Now, so to calculate these, extreme climatic events over the region, we require a daily time series of data. For the baseline, if we want to calculate it for the future, we require a future climatic simulations. For our study, we were interested in seeing the climatic extremities over baseline and a future climate scenario. So we used the ensemble simulations of a climate from the PRECIS RCM, simulated, at Indian Meteorological Department, jointly with the Hardley Climate Center. They have a horizontal resolution of about 50 square kilometers over the Southeast Asia domain, and we used our Climatex software to calculate all these 27 co-climatic indices. This software is developed by National Climate Data Center, NOAA. So these were extracted over the Kashmir Himalayan region on the basis of 14 grids. There were some grids where there was a lot of homogeneity. So these grids were clumped together so as not to replicate the data. So far as these are the list of the climatic extremities, over the region, we have the 16 core temperature indices. We have the cold spell duration indicator, diurnal temperature change, frost days, icy days, growing season length. We have the summer days where we have a temperature beyond 25 degrees Celsius. We have the tropical nights where we have the minimum temperature beyond uh, uh, 20 degrees Celsius and all that. And then we have the other parameters. And then likewise, we have had the indices for the precipitation parameters. We have the consecutive dry days, consecutive wet days, precipitation total, maximum for 1 day precipitation, 5-day precipitation event, precipitation day whereby we had a 10 mm of rainfall, 20 mm of rainfall, and so on. So far as the results for the baseline were concerned, there was no significant change, no significant climatic extremities, except the fact that like temperature parameters, they were showing a positive trend, positive slope, sorry, but the trend was not significant. Rest of the parameters, they were showing a negative trend and even negative slope, and even the trend being non-significant. So far as the parameters for the precipitation pattern for the baseline, that means that was taken as 1961 to 1990, was concerned. Again, if you see the precipitation parameters, they show a bit, positive slope, even though the trend being positive, but not significant. As we moved from baseline towards our future climatic scenarios, the scenario started changing. If you see, we saw an cold spell duration indicator, CSDI, it showed a decrease. That means over the years, the long winter months will start decreasing. Similarly, we have the DTR. It showed an increasing slope with the trend being positive. That means there will be a strong gap between the night and day temperature. Likewise, frost days. It was decreasing with a significant trend across all the grids of a Kashmir Valley. Tropical nights, whereby we will have a minimum temperature that will exceed 20 degrees Celsius. Under future climatic scenarios, it was seen that the valley grids, the grids towards the valley, are showing the signs of having a tropical night. And likewise, if we see the precipitation parameters, they also showed a significant change, even though there was not significant slope, in terms of precipitation. Overall precipitation over the valley is showing a decrease under the future climatic scenario. But there was one significant thing that we noticed it under the future climate is that the number of precipitation days, if you see the precipitation, 5-day precipitation or a 10-day precipitation, it starts decreasing. And there's a significant increase in a 1-day precipitation. That means there's not significant decrease in the precipitation, but the number of days in the precipitation under the precipitation event are decreasing. That means all the rainfall will be concentrated towards the 1-day precipitation event over the region, adding more towards the extremities over the region. So if we conclude, we saw a marked change, both in the extreme precipitation and the, temperature patterns. Particularly, they becoming noticeable towards the future scenario. The extremities associated with the baseline, though they were positive, they were not significant. However, the extreme associated with the future temperature indices were perceived to be statistically significant. Also, the analysis of the data showed that the extremities that are associated with the valley stations, they show an extremities with respect to the temperature patterns, while those of the high altitude stations, they show an extremity with respect to the precipitation and the minimum temperature events. Nevertheless, this prediction of these climatic extremities, they give you an understanding of a changing climate over the region, but the reliability of these extremities depend upon the data that we are using, whether we are using an observer or whether we are using a future climatic scenario. Thank you.
Thank you, Dr. Muhammad Muslim, for this very presentation on climate extremities. I think time is over. We should conclude the today's session.
Yes, Dr. Feroz, many thanks to you for moderating this session.
Thank you, sir.
Thanks to all for being us. Dr. Khan in the forenoon, Dr. Fozia Kazi in the session. Again at 6 p.m. This time we are going to close the meeting. Thank you.